Hi guys, in complex analysis, I was discussing various theorem based on the various formula. Up to the last lecture, I discussed Cauchy's inequality. Cauchy's inequality. In which I discussed if we have a circle C with center z minus a equal to capital R, and function is analytic in this circle, and also fz is bounded, means less than or equal to m1 c, then I told you if we take the modulus value of function at point z, so this is if a point at point A, that is the center of circle, this is always less than or equal to m factorial n upon capital R to power n. This was the Cauchy's inequality. On the last lecture, I proved this, and that is very useful inequality in future. We use this inequality in some numerical problem as well as to prove some theorem. In this part, two theorems are left today. First, I will take Lioville's theorem. Lioville theorem, first thing. And then fundamental theorem of algebra. Only these two theorems are left according to the curriculum and syllabus of complex analysis of your part. First, we take the statement of Lioville theorem, then its proof. Statement: if function fz is analytic for all finite points for all finite values of z, and is also bounded, then we have to prove that this function fz is a constant function. Actually, this is the statement of Lioville theorem. If any function is analytic for all values of z, so we can prove this. We take a large circle of radius r, and there are a number of points, means number of values of z lying in this, and so we have to prove if there is given that fz is analytic in this region, number one. Number two, fz is bounded, then we have to prove that function is constant. So proof of this theorem, first we take proof. That is very simple. If we use Cauchy's inequality, which I discussed on the last lecture, if we use this, so by the application of this inequality, we can prove Lioville's theorem very simply. Also, there are a number of methods to prove this. Some we can use Cauchy's theorem, which is out of the syllabus, and also some theorem. But this is very simple. If we take C be a circle, if we take C be a circle with center at origin and radius, that is large radius, means large circle R, and we suppose that z is any point inside C, then given that two things: one, fz is analytic in C, and fz is bounded, means mod of fz is less than or equal to m on C, where m is a positive constant, where m is a positive constant, right? Two things are given, and now you have to prove that fz is a constant function. So by Cauchy's inequality, we can take mod of first derivative f dash z is any point, is less than or equal to m, because n is 1, upon r. By Cauchy's inequality, we can take this. This is for first derivative. Here n is 1, right? And here we assuming that C circle is mod z equal to r, and r is large. R is large means r tending to infinity, means large circle means r tending to infinity, number one. Number two, what is the physical meaning? That this circle is containing a number of points of z. Yeah, you can say it will cover all the values of z for which fz is analytic. So if we take r tending to infinity, we get f dash z equal to 0. And you know that simple differential calculus theory, if derivative of any function is 0, then this implies that fz is constant for all z, and that is your proof of the given theorem. A function is analytic for all values of z lying in a closed region, and function is bounded, then it will be a constant function. This was the Lioville theorem. You see that proof is very simple and very short by using Cauchy's inequality. Right now, second theorem, that is the fundamental theorem of algebra. Fundamental theorem of algebra. This is the you can say this is the last theorem of this module, complex analysis 1. What is again a statement of this theorem? The statement is every polynomial of degree greater than or equal to 1 has at least 1 0. Only this is the statement, 1 0 in a region C. This is the statement of fundamental theorem of the algebra. Every polynomial, you know that polynomial algebra, of degree greater than or equal to 1 means you are taking here polynomials of whose degree 1, 2, 3 and so on, means linear polynomial, quadratic polynomial, cubic polynomial and so on, has at least 1 0 in region C. In other words, also this statement can be taken, you can say, in other words, we can say, if we take polynomial of degree n, in other words, we can say a polynomial of degree n has exactly n zeros. In other words, you can state fundamental theorem of algebra as, if we take a polynomial of degree n, then it has n zeros. Now we prove this. To prove this, first of all, I want to discuss some about very few about zeros, because in next chapter, in second module, complex analysis 2, there is a chapter in which I will discuss zeros, poles, singularities in detail. But simply, what is the meaning of zero? Zero means if fz equal to 0 and find the solution of these, and these values, these roots are called zeros of fz. That is sufficient to understand proof of this fundamental theorem here. And later I will discuss in detail if we put fz equal to 0 and then we get an equation in z, solve this, calculate this, then you will get different values of z, or you can say roots of z, and these roots are known as zeros of fz. Now, come on the proof of this theorem. For the proof here, we take a polynomial fz whose degree is greater than or equal to number 1, and also we suppose that if the fz is has no zero in C. For proof, let fz be a polynomial of degree greater than or equal to 1, number 1. And also, suppose that fz has no zero in given region C. That means fz is non-zero at z equal to 0. Fz is non-zero for any value of z, you can say for all z in C. Like this is our consideration. Means we are considering here fz is a polynomial greater than or equal to 1. Means the fz is a polynomial at least its degree is 1. And second thing I am considering here, the fz is fz having no zero for all z. Now I will prove this by the method of contradiction. You know that in mathematics, logical, there is a method of contradiction in which we assume something and we solve step by step. After some step, we see that we will get contradiction. So we say that our assumption is wrong and correct is this. So by contradiction, I will prove this. Fz is non-zero, and also given that fz is a polynomial, so fz is analytic function in C. So if it's I take its reciprocal 1 upon fz is also analytic function in C, because fz is analytic. You know that reciprocal of analytic function is always analytic. And also fz tending to infinity as z tending to infinity, because fz is polynomial. If this is, then 1 upon fz is 0 as z tending to infinity, because you know that 1 upon infinity is equal to 0. Z infinity. If 1 upon fz is 0, when you are taking z tending to infinity, z is large value. So from here we see that fz is bounded in C, because its value is finite at infinity. 0 is a finite value, defined value that exists, and so fz is bounded. If fz is bounded, this means by Lioville's theorem, I just stated and proved Lioville's theorem, if function is analytic and function is bounded, then it is constant. So this shows that fz is a constant function in C by Lioville's theorem. by Lioville theorem. And so, if it is constant means the fz is a polynomial of 0 degree. You know that the constant function is polynomial of 0 degree, and for polynomial of 0 degree, so fz is which contradict our assumption, because we consider that fz is a polynomial of degree greater than or equal to 1. Polynomial of 0 degree is that means which contradicts our assumption. Hence, we can say that fz has at least 1 0 in C, right? That proves your theorem. Okay, if fz is constant function means this is a polynomial of 0 degree, which contradicts our assumption, because in starting I have considered the fz is a polynomial of degree equal to or more than 1, and we consider the fz has no 0. So this contradicts our assumption. So we must have fz has at least 1 0 in C, and that proves your fundamental theorem of the algebra. This is the last theorem of this first module, and now you study these theorems and check this, and these theorems will will be used in coming chapter of complex analysis volume 2, and also use some numerical sum. Now in complex analysis volume 2, there are also some theorems, some formulae which I have to prove, in which first I will take up the first topic from here. Now we are going to start your complex analysis volume 2. That is the second module, in which first thing is expansion of complex functions. First thing is expansion of complex functions. Means in this topic we have discussed about the expansion of given complex functions, and for the expansion in form of infinite series. Here we have to, if we have fz, then this will be expanded in form of series z plus z square plus z cube and so on, like that, or you can say z minus a square and so on. Such type of infinite expansion, these are infinite series, you know that, right? So here we use two theorems in your expansion. One is Taylor's theorem and another is Lorentz theorem. So today, first I will take up Taylor's theorem, by which you can expand any complex function in form of infinite series. First statement: if fz is an analytic function, in a circle C with center point A and radius R, then fz can be expanded as, that is, fz equal to f of A plus z minus a f dash a plus z minus a square upon factorial to f double dash a plus so on nth term z minus e to power n factorial n fn of a plus up to infinity. This is Taylor's theorem, right? Here you are expanding functions, expanding function. This where z is a where in this expansion z is any point inside C. This is important. Z is lying in given circle in region of integration, region of analyticity. Right? This is the Taylor's expansion. You can say that this is Taylor series, and this is expansion of given function about point A, or you can say this is expansion of fz in ascending powers of z minus a. First, you can expand any complex function by using this Taylor's theorem. Before how you can use this, what is the application of this? We take its proof that is also part of your curriculum. How you can prove this? Here we have a circle C with center point A. To prove this, we consider, and Z is a point, Z is any point C, we consider another circle C1 about Z, in which Z is lying. Alright? So first, to prove this, let Z be any point inside C, and we consider a circle C1 inside C and containing point Z with center point A, right? Such that mod W mod Z minus A is less than W minus A. Means distance of Z from A is less than, this distance is less than the radius of this arbitrary circle C1. And from here you will get mod Z minus A upon mod W minus A is less than 1. That is mod Z minus A, W minus A is less than 1. And by this inequality, we can prove the statement of Taylor's theorem very easily. And also, I want to tell you there are a number of methods to prove this, but we are taking very simple method. And this is also a method whose theory you can use to solve the numerical sums very easily. How? If we take W minus Z, then we can take as, subtract A, add A, take as a common W minus A, we get Z minus A upon W minus A whole power minus 1 if you take it in numerator. Then by binomial theorem here, this is 1. So by binomial theorem, you can expand this, that is 1 minus 1 is plus, all terms must be positive, that is 1 plus z minus a w minus a plus z minus a w minus a square and so on, z minus a w minus a power n up to infinite. This is Lioville theorem because this term is less than 1, series is convergent, and so this thing. And now this is further open that is 1 minus w z minus a upon w minus a square z minus a square upon w minus a whole cube plus so on z minus a to power n w minus a to power n plus 1 plus 1. Now this is infinite series and radius of convergence is less than this, so this is uniformly convergent. Now we multiplying 1 upon 2 pi I into Fw. If we multiply by this on both sides and then integrating with respect to W over circle C1, we get left hand side is 1 upon 2 pi I integral C1 Fw upon W minus Z dW. That is the left hand side term. Now in first term, W minus A is here, integration is W. This is 1 upon 2 pi I integral C1 Fw upon W minus A dW. This is the first term on the right hand side. Similarly, in second term, integration is with respect to W, so take Z minus A is outside of the integration upon 2 pi I integral C1 Fw upon W minus A whole square dW. That is the second term. Similarly, third term, again take outside Z minus A whole square of the integral upon 2 pi I integral C1 Fw W minus A whole cube dW plus 1. Now nth term Z minus A to power n 2 pi I integral C1 Fw W minus A power n plus 1 dW plus 1. Right? And now in left hand side and right hand side, because Fz is analytic in C1, so by Cauchy's integral formula, we have already proved this. We know that nth derivative of f and z equal to factorial n 2 pi I integral c Fw upon W minus Z to power n plus 1 dW. Right? This is the Cauchy's integral formula I have stated and proved. Use this from left hand side to right hand side. The left hand side is Fz. Right hand side first term according to this formula Fa. Second term Z minus A into F dash A. In third term, if you multiply factorial 2 and dividing factorial 2, so this is Z minus A square upon factorial 2 F double dash A and so on. Nth term Z to power n. Again, you multiplying by factorial n and divide factorial n. This is Fn A plus so on up to the infinity. And this is the finally proof of Taylor's theorem. If you compare this, if you see that right hand side of the Taylor's theorem, so this proves the Taylor's theorem, right? This was the first theorem which will be used to expand any complex function in ascending powers of z. And now in this lecture, I am just finishing up to this proof. And next lecture, first I will discuss what is Lorentz series, and also I will give you some concept of convergence of such type of power series, because all of the proof and all the expansion of Lorentz series and Taylor series will depend upon the convergence property of the series. Okay, thank you.